What is up, multivariate gang? Today we are going to be talking about loci in 3 space. I think I forgot to mention this in the last video. When I say 3 space, I'm talking about 3-dimensional space, like with the XYZ coordinate system that we talked about. When I talk about 2 space, I am just talking about that XY coordinate system that you guys are already familiar with. Alright, so what is a locus? I believe you guys did some stuff with loci in geometry. But let's just go over it again, because this idea is fairly important. A locus is the set of all points for which given conditions are true. All the graphs that you guys have dealt with so far have been loci. They have been points for which the statement y equals f of x is true. So like, take for instance, y equals x squared. Like, we know that this point is not part of the locus because y does not equal x squared at this point. Like if that was like, I don't know, like 3, 1 or something, y does not equal x squared at that point. But at this point, let's say that that's 2, 4. It's not really, I know, but let's say it is. Y does equal x squared, so we know that that point is on the locus. All right, there are essentially 4 types of loci. There are points, whenever individual points are the only points that meet the given conditions. There are curves, which you guys know as graphs, which are, well, you know what those are. Those are one-dimensional squiggly thingies that meet the given conditions. There are surfaces, and you guys know what a surface is. It's like a sheet of paper, and all points on that sheet of paper, for whatever reason, meet the conditions. And we'll talk more about surfaces later, and which surfaces meet conditions, and yeah. And then there are solids. Like if you've got a cube, and for whatever reason the cube and all points within the cube meet the conditions set aside for the loci. This is really not that important. All you guys are going to be really dealing with are curves and surfaces, but like mostly curves. At least that is my understanding at this point. All right. And of course, if you guys don't remember this from geometry, this is like all points 3 centimeters from A, B, like this. This one's 3 centimeters, and this one's 3 centimeters, and this one's 3 centimeters. You know, and all these points make up this curve on the outside. It's called a slot. This particular shape with straight sides and then a curve. That's called a slot, for those of you who don't know. Yeah. So, first locus we're going to talk about are cylindrical surfaces. This is a surface, meaning if you have a point on the surface, if you have like a little dot on the surface, you don't want it to move around. It could go up and down, and it could go left and right. Unlike on a curve, if we were on a squiggle, and we had a dot on a squiggle, the dot could only go along the curve. could only go this way on the curve or this way on the curve. But that's not important right now. What kind of is? All right. So cylindrical surface. What is a cylindrical surface? It's a locus. So it's a collection of points that meets a given condition. So what is that condition that cylindrical surface meets? Well, it depends. So this cylindrical surface meets the condition z equals y squared. That's a parabola. It is a parabola. So if you're in two space, except not normal two space, instead we've got our y and our z axes. You've got the parabola y. Nope, z equals y squared. All right, this is the parabola that meets this condition. And we know that this is true when x equals 0, that this parabola exists in the yz plane. But we also know it exists where x equals 1. Why do we know that? Because z equals y squared. Right? So no matter what your x is, as long as z equals y squared, as long as a point meets the condition z equals y squared, that point is in our locus. So x equals 0. The zy plane, or the yz plane, our parabola meets the condition in that plane. Same with x equals 1. Same with x equals 2. Same with x equals negative 1. Same with x equals negative 2. Same with x equals like 0.1. X equals 17 million. X equals the square root of whatever the heck. Does not matter, as long as z equals y squared. So what happens is our locus is this parabola, and it's this parabola, and it's this parabola, and it's this parabola, so what we get is this extrusion of a parabola along the z-axis. So we can define a cylindrical surface as any 2D curve that is extruded along the axis perpendicular to the two axes involved with the curve. So here, this parabola is defined by z and y. Therefore, we can extrude z equals y squared along the x-axis, and we get this shape right there. All right. Now, why is it called a cylindrical surface? That's really important. Why is it called a cylindrical surface? Well, the reason it's called a cylindrical surface is because if you have the graph, say, of x squared plus y squared equals 1, or a unit circle, we know that that includes this circle, because x squared plus y squared equals 1 for all points on that circle. But we also know that's true for this circle of radius 1. And true for this circle of radius 1, and true for this circle of radius 1, true for this circle of radius 1, and this circle of radius 1, and all the circles in between, and all the circles going to infinity and beyond. So what we eventually get, if we draw enough of these circles, is we get a really ugly looking, what we get is a cylinder. It's a cylinder. When you extrude a circle along an axis perpendicular to that circle, or perpendicular to the plane that holds that circle, you get a cylinder. That's why these are cylindrical surfaces. Alrighty, good job guys. That's all we got. Keep on mathing.